Hi, I'm presenting our work on improving equivariance in state-of-the-art supervised depth and normal predictors. This is joint work with Anand, Yusheng, and David at University of Illinois, Urbana-Champaign. What is equivariance? Equivariance means the output transforms in the same way as input. Many dense image regression tasks, such as relative depth and normal prediction, should have equivariance to resize cropping transform. Are state-of-the-art depth predictors equivariant to cropping? Let's look at this famous Midas depth prediction network. As I vary the input crop, the output depth prediction actually varies a lot. Notice that I have already least square aligned the predictions, so the effect of camera center and size change is already accounted for. The same issue occurs with surface normal predictors. If I take two image crop of this left image and feed them into either a depth surface normal prediction network, the output have structural inconsistencies highlighted in the yellow boxes. To address the non-equivariance issue, we propose an equivariant regularization approach. We first use data augmentation to sample a few crops, then compute the average of F. Next, we impose an equivariant loss between the average output and each crop's output as an regularization term. Here is an illustration of our equivariant regularization approach. For this input image, we can have three different random crops. We feed all of them into the network F to get some kind of feature map. Then we take the average of the three by aligning them to their proper locations. We can take the corresponding crops from this average feature map and use them as a target in the equivariant L2 loss. The individual feature map can also be supervised at the same time by the user supervised learning loss. There are several benefits of the equivariant regularization approach. It is quite general, so it can be applied to any network, including CNN and transformer. It is flexible in that you could control the strength of your regularization by a loss coefficient. It is efficient because in test time there's no additional cost, so everything is done during training. Let's have an approach with this taxonomy dataset. This is a very rich dataset. We mainly focus on depth and normal in our paper, but the same idea can be carried over to other dense prediction tasks. Here are the supervised learning results on taxonomy. We have baselines with or without augmentation. On top of data augmentation, if we add equivariant loss and regularization, there are further decent improvements. Our equivariant regularization can also leverage unlabeled data. So in this semi-supervised setting, we only label 1/4 or 1/2 of the dataset. We can see that the equivariant loss can leverage the unlabeled dataset to further reduce prediction error. Finally, we use our equivariant regularization loss in an unsupervised fine-tuning setting. So we take the Midas depth predictor and fine-tune it without using the ground truth label on NYUV2. So this is the result. In the bottom, we can see that as I vary the crop, the after fine-tuning version actually has much more consistency across different crops. To conclude, our paper points out and address the overlooked equivariance issue in depth and normal networks. Thank you.